came to look at birds. So far, swamp sparrow, blue-gray gnatcatcher, which is a gorgeous little bird, song sparrow, hermit thrush. I thought I had a rusty blackbird, but I think it was just a grackle. And it's a day where we could start talking about air pressure. I haven't quite figured out how I'm going to make an air pressure video, but this could be just a beginning. Because on a day like today, we have what would be considered high pressure air that has filled the region. The earth is heated unevenly, day after day, night after night, all the time, heating, cooling, and there are pockets where the air is rising because of its heating, rising off the surface of the earth, and where the air rises off the surface of the earth, we say there's low pressure. And then there's pockets where the air is sinking, and that air that's sinking is cold because it's coming from high up in the troposphere, and it's sinking down, and that would be a day like today, and we call that air high pressure air. And the difference between the high pressure zone and the low pressure zone creates the wind. So over the last 24 hours, we had a pretty windy set of conditions, and that wind was caused by the high pressure that's here today chasing the low pressure that had headed through our region Thursday into Friday. So it turns out on the North American continent, there are pockets that are frequently the source of low pressure air, and there are areas, pocket zones, that are frequently the source of high pressure air. And for New York City, the two most important of these zones would be down in the Gulf of Mexico to our south and slightly west, and over central Canada to our north and west. And these are sources of low pressure air from Gulf of Mexico and high pressure air from Canada. It is then global winds in relation to the rotation of the earth and the Coriolis effect that brings us a movement of air that is predictable. For the weather, we often talk about air pressure in relation to two other units. One, inches of mercury, and two, millibars. Inches of mercury comes about from the way in which people first discovered that air pressure was something that was fluctuating, changing. And they began to see patterns in the change of air pressure in relation to the weather. And the great idea was to take a bowl of mercury. And mercury, if we remember, is liquid. And if you take a bowl of mercury and you put a metal tube in it, a glass tube, why did I say metal? A glass tube in it. If the pressure of the air is high, if the air is descending onto the bowl of mercury sitting out in the air, that mercury will be pushed down, and the glass tube that is standing in the bowl of mercury will have mercury rise, and therefore the pressure is said to be rising. And how much is it rising? It's rising a certain number of inches of mercury. And so when we see the weather reported, for instance, on the weather variables that I've asked you to be looking at, you'll often see 29.92 inches. Well, that's inches of mercury. So the millibar is simply the metric equivalent of inches of mercury. Standard air pressure at sea level, the equivalent of 1 atmosphere, is around, I believe it's about 1,000 and 13.1 millibars, if I remember correctly. And in inches of mercury, I believe it's somewhere about 29.92. That's the standard air pressure for conditions at the surface of the earth at sea level. Air pressure rising from that standard generally means the weather is getting nicer, and air pressure lowering from that standard usually means that the weather is turning stormy. The basic tool of determining air pressure that you're responsible for knowing the name of is the barometer. The same way we have a tool for temperature, the thermometer, and a tool for humidity, the sling psychrometer, so we have a tool for measuring air pressure, the barometer. Barometer, and bar or baro coming from, I believe, the ancient Greek, meaning pressure. And so please be aware that that word, B-A-R-O-M-E-T-E-R, the barometer, is the tool used to measure air pressure. And typically, barometers report the result of the measurement in either inches of mercury or millibars. You'll see on page 13 of the reference table, let me put this up here a little bit, that there's a way to convert between millibars of pressure and inches of mercury. So you should become familiar with that chart on page 13 that allows you to move between the two units. On the right hand side, we can see where we can convert between inches of mercury and millibars. Use this chart. One of the ways that we like to think about air pressure is by assessing the rising and falling of air masses, well, not really air masses, but the rising and sinking, I should say, of air from the surface of the earth at different latitudes. And a way to understand this is found on page 14 of the reference table with a diagram that you've looked at before, we've looked at before together, of global winds. And when you look at that diagram, you can't help but notice that there's a pattern to air circulation up and down off the surface of the earth and then back down onto the surface of the earth, creating winds that flow over the surface. And I'd like you to take the moment to look at the reference table and to investigate how the air rises from the equator and travels north to about the latitude of 30 north, and south to the latitude of about 30 south, and then begins to sink. And it is at that zone of 30 north and 30 south that we have generally a swath, a belt, that's the best word, a belt of high pressure all around the earth. High pressure air tends to accumulate as it sinks down at around 30 north. Likewise, we have a zone of low pressure air at the equator, which explains why it's rising from the equator. Then, oddly, we have another zone of low pressure air at 60 north and south, with the air rising from there and then heading south and sinking at 30, and heading north and sinking at the poles. So there's a pattern to air rising and sinking that then creates belts of pressure, low and high, around the earth. A belt of low pressure around the equator. A belt of high pressure at 30 north and south. A belt at low pressure at 60 north and south. A belt of high pressure at the poles. And this is a story of global pressure, which then impacts global winds, with wind blowing from those belts of high pressure to those belts of low pressure, and of course controls the movement of air masses, cold and dry, warm and moist. So one of the things that you can see here in the planetary wind and moisture belts in the troposphere diagram from page 14 of the reference table are those lines over the surface of the Earth that are moving from zones of high pressure at 30 north and south and at the poles towards zones of low pressure. Those are the global winds. You have southwest winds, northeast winds, southeast winds, northwest winds moving from north to south. Then around the outside of the globe are convection cells, which are illustrating the rising and sinking of air around the surface of the Earth. So one of the last things that we should think about here when we're thinking about pressure is in relation to page 14 of the reference table again, and the fact that you see these curved lines on that diagram that indicate a pattern of global wind. And you'll notice that there are winds blowing from the belts of high pressure towards belts of low pressure. That is the way that wind behaves. And that diagram on page 14 of the reference table can help you to understand the predictability of the wind, and therefore the way in which we can also predict aspects of the weather. So belts of air pressure creating global winds. One more thing that I wanted to mention that I forgot to in my previous air pressure discussion, and that was that these bands of low and high pressure that exist around the world, starting at the equator and heading up to the poles, north and south, they are part of what are called cells of air movement. Air moving up from the equator, high in the troposphere, spreading north towards 30 north, spreading south towards 30 south, and then sinking and flowing over the surface. And that convection has a special name called a Hadley cell. There's actually Hadley cells and Farrell cells, and they are all convection cells moving air in the atmosphere. It's three sets of convection cells, as you can see in this picture. Hadley cells rising at the equator, Farrell cells rising at 60 north, and finally polar cells rising at the same 60 north. One of the things that's maybe a little bit difficult to visualize when I talk about a convection cell is the fact that it's three-dimensional. Three-dimensional, heading up from the equator into the upper atmosphere troposphere, and then crossing in that upper atmosphere north to about 30 north or 30 south and sinking. Again, a three-dimensional cell of consistent air movement, predictable and deterministic in the sense that it shapes and determines the weather. It's quite beautiful here today, Saturday, high pressure. Nope, people not gonna follow the rules here. They don't want to social distance.